Lesson 8. Combined Loading. A real member rarely carries just one thing. A shaft bends and twists at once. A bracket pulls and bends at once. The move is always the same 2 steps. At one chosen point, add the like stresses. Every normal stress into a single sigma. Every shear into a single tau. And only then feed that state into Mohr's circle for the principles and the maximum shear. Superpose first, transform second. Here's the problem. One round shaft, one section, carrying a bending moment and a torque together. At the worst point on the surface, find the combined normal stress, the shear, the 2 principal stresses, and the maximum shear. Bending gives a normal stress. Torsion gives a shear. We combine them at a single point, then read the extremes off one circle. Concept 1. Combine like with like at one point. First, superpose the elementary stresses from each load. Every normal stress from axial pull and from bending adds into a single sigma, and every shear from torsion adds into a single tau, all evaluated at the same physical point. Second, hand that one combined state to the transformation from last lesson. The order is not optional. The transformation is nonlinear, so it has to act on the stresses after you sum them, never before. Concept 2. Pick the critical point. Stresses vary around a section, so evaluate them where they add up worst. On a bent, twisted shaft, that's the outer fiber. Bending peaks there. Torsion is uniform over the whole surface. And, key point, the transverse shear from the shear force is 0 at the outer fiber, because its area moment vanishes there. So at that point, the only shear is torsion, and the state is one normal stress along the axis, plus that torsional shear, with the perpendicular normal stress 0. Concept 3. The round shaft shortcuts. Plug the circular section properties into the elementary formulas, and they collapse to 2 compact forms. The bending stress is 32 m over pi times d cubed, and the torsional shear is 16t over pi times d cubed. Nothing new, just mc over I and tc over j, written for a solid circle. And because the polar moment is exactly twice the bending moment of inertia, the torsion constant is half the bending one. Setup. Write down the diameter and the 2 loads, then leave blanks for the 2 surface stresses, the circle center and the radius. Because the perpendicular normal stress is 0, the center collapses to half the normal stress, and the radius is the radical of that half in the shear. Compute those 2 and everything else is center plus or minus radius. Solve. Part 1. The 2 surface stresses. Bending through the compact form gives the normal stress. Torsion through its compact form gives the shear. That leaves a plane stress point with 1 normal stress along the axis, a 0 normal stress across it, and the torsional shear. That single combined state is what we feed into the circle. Solve. Part 2. Build the circle and read the principles. The center is half the normal stress. The radius is the radical of that half and the shear. Here the 2 legs form a 3, 4, 5, so the radius is a clean 50. The principal stresses are center plus and minus radius, 1 tensile, 1 compressive. A bent, twisted shaft point almost always has 1 principal stress on each side of 0. Solve. Part 3. The maximum shear, and here's the trap the exam loves. The maximum in-plane shear is just the radius, but a free surface adds a 3rd principal stress equal to 0, out of plane. Sort all 3, 90 on top, then 0, then minus 10 at the bottom. The absolute maximum shear is the largest principal minus the smallest, halved. Since the compressive principal is more negative than the out-of-plane 0, the in-plane circle already reaches from the highest to the lowest principal, so the in-plane maximum and the true 3-dimensional maximum are the same value. The out-of-plane 0 is the middle principal, not the minimum. Final answers. Bending stress 80, torsional shear 30, center 40, radius 50, principal stresses 90 in tension and minus 10 in compression, and a maximum shear of 50, where in-plane and absolute agree. And the fast check. The 2 principal stresses add back to 80, exactly the original sum of normal stresses. That total never changes when you rotate the element. Traps. 3 ways combined loading bites. 1. Add like to like first, every normal stress into a single sigma, every shear into a single tau, all at the same point. Never mix a normal with a shear. 2. Transform after superposing, never before. The principal formula has a radical, so it's nonlinear. You cannot take principles load by load and add them. One combined state enters the circle once. 3. Pick the critical point. Bending peaks at the outer fiber where transverse shear vanishes, while the neutral axis has peak shear but no bending. Check where the combination is worst, usually the outer fiber. Quick recall. Superpose, every normal stress into one sigma, every shear into one tau. For a round shaft, those are the two compact forms. With the perpendicular normal stress 0, the center is half the normal stress, and the radius is the radical of that half and the shear. Principal stresses are center plus or minus radius. The maximum in-plane shear is the radius, and the three-dimensional maximum uses the largest and smallest principal stresses. Sum like stresses first, then transform once. Next up, Lesson 9, Strain Energy and the Stress-Strain Curve. We can now assemble a stress state from several loads and read its extremes with Mohr's circle, which closes the analysis half of the week. Next, we move from stress to energy. How much work a loaded member stores, read directly off the stress-strain curve. Elastic strain energy, resilience up to yield, and toughness all the way to fracture. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.